Okay. Um, good good evening. My name is Sanvi Sinha, and I'm from Bangalore International School.
I'm Manushri Danakoti, and I'm also from Bangalore International School.
And I'm Trisha Lad, and I'm also from Bangalore International School.
So the problem statement we've chosen is efficient cells using quantum physics. The contents we'll be exploring would be the different types of solar cells used, and in the end, we'll compare the best and most efficient type of solar cell. So we'll be beginning with tandem solar cells. What are they? They consist of multiple layers of semiconductors arranged in a series with different band gap energies. Band gap of a semiconductor is the minimum energy required to excite electrons in their bound state for them to participate in conduction. So the band gap can be represented in this diagram, where it is the difference between the conduction band and the valence band. And bands are composed of closely spaced orbitals. Each layer can absorb a range of wavelengths so that the solar spectrum is used most efficiently. Tandem solar cells can be designed with materials of different band gap energies to maximize its efficiency. Silicon and semiconductors like gallium arsenide can also be used in a tandem solar cell. Charge carrier selective contacts. So before we understand what these type of cells are, we must understand what charge carrier generation and charge carrier recombination is. Charge carrier generation is when electron-hole pairs are created by exciting a valence electron from the valence to the conduction band. Recombination is the reverse process of generation, where electrons and holes of conduction from their valence band where electrons and holes from conduction from their valence band recombine and are annihilated. Recombination reduces the efficiency of conventional solar cells, and this can be seen in the diagram where energy is lost from recombination and gained by generation. So these cells are more efficient. Charge carrier selective cells are more efficient because they use materials with different electronic properties as compared to conventional solar cells. These varying properties allow the system to extract electrons or holes from the solar cells selectively based on the requirement of the cell. The recombination losses are then reduced as the amount of energy loss decreases and the cell is more efficient. The diagram shows a simple structure of a charge carrier selective contact, and you can see how it's usually made of silicon and other layers. Okay.
So next I'm going to be discussing the perovskite solar cells. So the perovskite solar cells work by converting sunlight into electrical energy using material with a perovskite crystal structure as the active layer. So what is a perovskite? The perovskite is a material with the same crystalline structure as calcium titanium oxide. So this is essentially a compound that has the chemical formula ABX3, where A and B represent the cation and X is an anion that bonds to both of them. On the right, you can see a diagram of this picture. Steps to generate electrical energy. So first, the photons are absorbed by the layer and energy transfers throughout the material to its electrons. This creates the electron hole pairs. Next, the perovskite layers and the adjacent layers generate an electrical field as the electrons are drawn to the electron transport layer while the holes are drawn to the hole transport layer. So the electron transport layer facilitates the movement of electrons to the electrode, while the hole transport layer causes the movement of the hole to the electrode. The electrons and the holes collected by the transport layers flow through the electrical circuit, generating electrical power. So the features of a perovskite solar cell. So one great thing about the perovskite solar cell is its promising future. And initially, it was found to have a 3% free efficiency in 2009. It later got to 25% today, which is similarly comparable to the traditional silicon solar cells. And this percentage is expected to continue to increase. And using the thin film fabrication techniques, the solar cell is able to be flexible and transparent. The technique involves adding thin layers of perovskite material onto a flexible or transparent substrate, such as plastic or glass, increasing the use cases for the solar cell, such as in wearable devices or on a window. Additionally, the perovskite solar cells are low cost due to the fact that it uses materials that are readily available, such as lead, and the production process uses roll-to-roll printing techniques, which can be scaled up to mass production with ease. This increases the efficiency of manufacturing. And additionally, the manufacturing the perovskite cell uses much less energy, as it can be made at room temperature compared to the silicon, which can be forged at around 3,000 degrees, making it much worse for the environment through the combustion process. Perovskites can function. Additionally, perovskites can function with even with numerous imperfections and impurities due to the fact that the performance is mainly determined by its ability to separate the charges. Quantum dots. So quantum dots are a man-made nanoscale crystal that exhibit unique optical and electronic properties, including the ability to transport electrons and emit light of various colors when exposed to UV light. So steps of the process include a quantum dots first get synthesized using various methods, such as colloidal synthesis and electrochemical processes. During the synthesis process, components such as the size, shape, and composition of the quantum dots can be controlled. So the quantum dots are then integrated into the solar cell structure using various techniques, such as spin coating, dip coating, or layer by layer assembly. Depending on the type of solar cell, a specific integration method is applied. Photons of different wavelengths then get absorbed by the quantum dots when light strikes the quantum dots, and this causes it to excite an electron within the dot to a higher energy level, creating an electron-hole pair. The solar cell contains an electrical field which separates the electrons in the holes, and the electron and holes collect at electrodes, which generate the power. And by adjusting various components, the quantum dots of the quantum dot, the efficiency can be optimized, such as by altering the size, composition, surface chemistry, and number of layers, as well as the integration of other materials. So the features of the quantum dot include that it has the potential to increase the maximum attainable thermodynamic conversion efficiency by solar photon conversion up to 66% by utilizing hot photo-generated carriers to produce higher photo voltages or higher photo currents. Additionally, it contains the ability to absorb light at multiple wavelengths, since the energy level of an electron in a quantum dot is quantized. Therefore, it can only absorb photons of specific energies, making it possible to create a material that can absorb a light at a broad range of wavelengths. Additionally, it's made pretty low cost due to its low cost materials, as well as its relatively simple manufacturing process that's additionally very inexpensive. And it can be used for long periods of time due to the quantum dot stability. And this is due to the quantum dots having a strong due to its electronic and structural properties, as well as its surface chemistry. And lastly, it has an incredibly high quantum yield.
Okay, next we have multiple exciton generation. Multiple exciton generation is a process in which a single photon with high energy is absorbed by a semiconductor material, leading to the generation of multiple electron-hole pairs, excitons, rather than just one. Typically, in a conventional solar cell, a photon with energy greater than the band gap energy of the semiconductor is absorbed, resulting in the generation of one electron-hole pair. However, in MEG, the excess energy from the absorbed photon is distributed among multiple electron-hole pairs, leading to the creation of multiple excitons. MEG occurs in semiconductor materials with high absorption coefficients, such as quantum dots or nanocrystals. When this process occurs in quantum dots, the energy of the absorbed photon in excess of the band gap can be used to create one or more additional excitons instead of being wasted as heat. So features of MEG, the first one is that it converts high energy photons. MEG allows for the efficient conversion of high energy photons to multiple electron hole pairs, increasing the overall efficiency of the photovoltaic device. The second one is that it conserves energy. MEG conserves energy and momentum in the system, allowing for the generation of multiple excitons with high kinetic energy. Third feature is that it's a multiple carrier generation. So MEG generates multiple carriers, which can be used to enhance the performance of photovoltaic devices, such as increasing the photo current and reducing the recombination losses. Then lastly, there's plasmonic solar cells. So plasmonic solar cells are a type of photovoltaic device that use plasmonic nanoparticles to enhance the absorption of light in solar cells. Plasmonic nanoparticles are metallic or semiconducting nanoparticles that can resonate with incident light, resulting in localized electric field enhancement that can increase the absorption of light in nearby materials. Plasmonic solar cells are made of thin film, crystalline silicon, amorphous silicon, and other types of cells. Advantages of plasmonic solar cells are that they increase light scattering, they extend light absorption to longer wavelengths, and they transfer the plasmonic energy from the metal to the semiconductor. Disadvantages are that substrates which are cheaper than silicon, like steel or glass, can be used, and they can't absorb light as much as thicker solar cells. Then there's the design of plasmonic solar cells. So the design of the cell varies depending on the method used to trap and scatter light. So first there's nanoparticle cells. Here, metal nanoparticles are deposited on the top surface of the solar cell. As light hits these particles at their surface plasmon resonance, light is scattered in different directions. This allows light to travel along the solar cell and bounce between the substrate and the nanoparticles, so the solar cell can absorb more light. Then there's metal film cells. Here there is a thin film of silicon and a thin layer of metal deposited on the lower surface. Light travels through the silicon and generates surface plasmons on the interface of the silicon and metal. This generates electric fields inside the silicon. If the field is strong enough, electrons can be moved and collected to produce a photocurrent.
Okay, now we'll be comparing the analysis. We'll be comparing the efficiencies of all these types of solar cells. The silicon cells in the graph are indicative of the tandem and the plasmonic cells. The multi-junction cells are indicative of the charge carrier selective contacts and the perovskite cells. The thin film is indicative of the perovskite solar cells and the plasmonic solar cells. And emerging PV is of quantum dots and MEG. So we can see a general trend in increasing efficiency over the years, but we can also see that multi-junction cells from 2010 took a leap in their efficiency. So we can see that we can conclude that multi-junction cells, such as charge carriers, selective contacts, and perovskite cells, are the most efficient out of all of these methods. So here are resources, and thank you.